Okay, now we got the answer to part A, that the pH of our buffer before we did anything was equal to 4.74. What we're going to do now is we're going to add 0.02 moles of solid sodium hydroxide to 1 liter of the buffer in part A. And one of the things that they tell us here, in addition to giving us the equilibrium constant for acid dissociation, is they tell us that assume the additions cause negligible volume changes. And you'll see how that comes into play here in our worksheet. So again, if we think about who's in solution, we still have our acetic acid, and it's 0.5 molar. We have our acetate ion at 0.5 molar. Again, our sodium ion, spectator, not anything that we're concerned about. And we actually are going to have some sodium that comes from two sources here. We have the sodium that would come from the sodium acetate, and then we have the sodium that's going to come from adding our solid sodium hydroxide here. So in either case, that sodium's not important. So we're not going to include it in any of our chemical reactions or our ICE tables because it's not relevant in that regard. The other thing that we have in solution, though, that is relevant is we have hydroxide. Now in this case, they don't give us a volume or a molarity of it. They basically just tell us that we're adding 0.020 moles of this. They do tell us in this case that we have 1 liter of the buffer solution. So if we have 1 liter of the buffer solution, now that we do have a volume of it, we can calculate the number of moles. Well, this is a pretty straightforward calculation here. 0.5 moles per liter times 1 liter means we have 0.5 moles. So this problem is pretty straightforward in that we know how many moles that we have. So we've got 0.5 moles of our weak acid, 0.5 moles of our conjugate base, and in our problem here we're going to add 0.02 moles of our strong acid, which contributes hydroxide. Okay, as I mentioned here, it tells us assume that the additions cause negligible volume changes, and that's fundamentally what makes this problem different from a titration problem, is we're adding the sodium hydroxide and assuming that the volume change is negligible. That won't be the case when we consider titrations, where we have the sodium hydroxide as a solution that you deliver from a burette. Okay, so again, continuing on with this worksheet, the chemistry that's going to happen is that this hydroxide here is going to react not with our base here. We're not going to have two bases react. The only combination that's going to have some chemistry happen is that our hydroxide is going to rip a proton off of our weak acid here and generate the conjugate base. So the chemistry that we can write here and the equation that we'll write is that we've got our weak acid, and when it finds a molecule or an ion of hydroxide, chemistry we always draw as one-way arrows here. This hydroxide ion is going to rip a proton off of our acetic acid, leaving behind the conjugate base and generating a molecule of water. So again, chemistry tables we write as ICF tables. Initial, change, final. And as it says here, we want to write an equation for any chemistry that's happening, prepare an appropriate ICF table, filling in the I row, our initial row, using moles of substance. So that's important. Our reaction tables contain moles of substance. And then propagating the change column using whoever is the limiting reactant. So let's put this in here and see if this makes sense. We know that we've got 0.5 moles of our weak acid, 0.5 moles of our conjugate base. We've got 0.02 moles of our strong base that we're adding. And in this case, we're going to assume that water is not really important and relevant to what's going on here. It tells us that our change column is going to be propagated and limited by whoever's the limiting reagent. Since all of this stoichiometry is 1 to 1 to 1, what this really means is that we're going to run out of our hydroxide first, which means we're going to use up all of that. Reagents go away, so we have a minus there, and then we use our stoichiometry to propagate that. In this case, since it's all ones, we propagate it as losing the same amount of acetic acid and gaining the same amount of the conjugate base. Just like you do with ICE tables, for ICF tables, the final column is generated by the sum of the initial and the change. So in this case, we've got 0.48 moles of our weak acid here. Our limiting reagent is going to be disappeared. So you want to make sure that whatever you set as your limiting reagent, you end up with none of it at the end. It completely reacts. And then 0.52 moles of our weak acid. And remember, this is qualitatively how a buffer works. If we added hydroxide to solution, we would change the hydroxide concentration if all we had was pure water, and that would significantly change pH. But because we have essentially an army of molecules, in this case, this is the army that reacts with our additional base. It sacrifices itself, we lose a little bit of it, but that neutralizes the base that we've added. And then it basically gets converted into its conjugate base counterpart. Now again, these problems become relatively straightforward because it tells us assume negligible volume changes. So we're going to say assume no volume changes, which means we still have 1 liter of solution. So we still need to convert these back into molarities, right? Because this says if your chemistry involved mixing substances that create a new larger volume, add these volumes together, and then use the above quantities in moles with the new volume in liters to calculate the new concentrations of all species. Well, we didn't add things together, but our new volume is still the same as the old volume, which is 1 liter. We get concentrations by taking moles over liters. So we can get the concentration of acetic acid that's new to be equal to 0.48 moles over 1 liter is 0.48 molar. We can do the same thing for this guy over here. The new concentration is equal to 0.52 moles in 1 liter, and that's equal to 0.52 molar. So now our problem is going to become pretty much similar to what we had in part A. So again, this was part A. But what's changed is we no longer have an equal concentration of both of these. We've diminished this guy a little bit and added this guy a little bit. So the rest of my problem here is going to look very similar to what we did in part A. So let's do this for part B and then we'll kind of compare. So once we know who we have in solution, right? Again, in solution, we've got some of our weak acid, our acetic acid, some of the conjugate base. The options available, since we've neutralized all of the addition of hydroxide, is just to have an equilibrium between these two. So the equation we want to write is that for acid dissociation, and as I just mentioned, this is going to be the same equation that we used for part A, but now the only thing that's changing is we have slightly different concentrations of our starting species. They were equal here before our chemistry started. They're a little bit different now that our chemistry has begun to proceed. So it's 0.48 molars initially of our weak acid, 0.52 molar of our conjugate base. We're going to assume that any contributions of H3O plus from water is negligible. Again, water does not appear in our ICE table. I'm going to treat this the exact same way, minus x, as we treated our last problem. So minus x plus x plus x. 0.48 minus x, 0.52 plus x, and x. Now, one of the things I'll note is sometimes people get confused when they start to write this, is they might write the equation starting with the conjugate base. So they might write an equation that looks like this. I'm just going to kind of write this down here in parentheses here, and we'll talk about this. So if you wrote this equation, and you said, all right, I've got an equilibrium between this guy and this guy. If this guy encounters water, and there's lots of it in solution, it's going to make this guy and leave behind hydroxide. And essentially, you'd set up the table very similar. This number would go over here, This number would go here. You'd still have your minus x's and plus x's, but what's going to be fundamentally different is you have to use the Kb value for this. For this one, because we wrote an acid chemistry that's happening, we use the Ka value. So again, we're given the Ka value for this problem. Remember, you can easily get to the Kb value using Kw and the relationship that Ka times Kb equals Kw. But sometimes people get confused because they don't know which of these equations you can use. I'll tell you, you can use whichever one you want. Keeping in mind that X, when you solve this ICE table, will give you H3O+, but again, you must use Ka. X, when you solve, will give you OH-, but again, you must use Kb. Do you remember when we did those problems where we kind of walked around the block between hydroxide concentration, hydronium ion concentration, pH, and pOH? That's essentially kind of what we're doing here with this problem. So there's no right or wrong answer. What I usually like to do, though, is whatever equilibrium constant they've given me, I try to write the equation that matches that. As we'll start to see when we do some titration problems, sometimes the only molecule you might have in solution is such that you have to write a Kb equation. So we'll see that in another future sample problem, but I just kind of wanted to highlight that. So this, again, is a little bit of an aside. I just want to make sure to write that's not kind of part of what we're considering now. So here's our ICE table. Again, looks very similar to what we saw before we added anything to our buffer solution. All that's different is those numbers are a little bit different. So we're going to treat this the same. We're going to use our Ka expression to solve for X. Since this value isn't really different, I'm not going to need to go through a pre-check again, but we'll solve for X, and then I'll also show how we can use the Henderson-Hasselbalch equation to solve this as well. So again, Ka in this case, and I'm going to already do my assumptions, so it's equal to X times 0.52 over 0.48. Propagating this and solving for X, X is going to be equal to 1.6615 times 10 to the minus 5th molar. And again, that's equal to H3O+ concentration. So pH in this case is equal to 4.78. And then, again, that's sort of expected. We did some chemistry where we add some hydroxide. We added some base to our buffer. Our army of weak acid and conjugate base kind of was able to help out here. In this case, our weak acid was what helped out, sacrificed itself, made a little bit more of the conjugate base, so we have no more of the hydroxide. But because we changed this ratio a little bit, our pH gets changed just slightly. Remember, our pH for this first one was 4.74. So what I'm going to do now is I'm going to just show you how when you have a weak acid and its conjugate base, you can use the Henderson-Hasselbalch equation. So Henderson-Hasselbalch again says pH equals pKa plus the log of the conjugate base over that of the weak acid. So again, negative log of 1.8 times 10 to the minus 5th plus the log, and again, in this case, it's going to be, the conjugate base is going to be 0.52 over 0.48. Remember, when we had this here in part A, the log of 1 is 0. The log of a number, so the log of a number greater than 1 is positive. As we'll see in our next problem, the log of a number less than 1 is negative. So kind of the number 1 is your tipping point with your log scale. Log of 1 is 0, log of something greater than 1 is positive, log of something less than 1 is going to be negative. But what we can see here is that our pH is going to be slightly increased because we've increased the ratio of conjugate base to weak acid. And again, we expected this. We expected to have our pH increase a little bit. Mathematically, kind of go through and work through this and you'll get the same answer. What we're going to do next is work through this problem. So we've got A, where we had the buffer just by itself. B is where we had the buffer that we added base to. And part C is now we're going to add strong acid to it. So working through that problem, I'm going to go a little bit more quickly because I'm going to assume that you've already watched parts A and B.